Now, let's look at an example of a subset of Rn, which is a subspace. So in this case, example, we've got a subset W of R3, right? And I know that it's a subset of R3 right away because I can see in the typical form of an element of W, it's got 3 coordinates. So that I know that anything in W is a three-dimensional vector. So I know that this is a subset of R3. But now the question is, does it satisfy the 3 conditions for a subspace? Well, remember, the first condition is that it must contain the 0 vector. Right? I'll just pull up the list of properties here at the end of last page, right? It's got to contain the 0 vector. That's property 1. Let's start by addressing that. So the first thing we'll do is which 0 vector are we talking about? If we're talking about a subset of R3, we want to know if this contains the 0 vector in R3. So that's going to be the first thing we look at. So let's write out the 0 vector of R3. It's the vector with 3 coordinates, all of which are equal to 0. So now, is that a vector in W? And how would you check? Let's study the definition of W, and let's try to do what we did last time and just say it out loud in words, right? I mean, you can say it as the set of all three-dimensional vectors x, y, z, such that y is equal to z, but how about we try to say it without referencing those variables? What is this equation y equals z really requiring of this vector? It's requiring the second and third coordinates to be equal. And again, I promise you, if you get in the habit of going through that process, it makes these problems so much easier. Because now, it's a little easier to tell. Is this vector in W or not? Well, just check if its second and third coordinates are equal. And certainly they are. They're both 0. So there's not too much to say for that first step other than just we make the observation that the 0 vector is in W. Okay, I wouldn't mention anything else or add more justification to that. I think it's fairly straightforward to see that. It's just based on the definition of W, it's automatic. Not automatic, I guess, but it's immediate that the 0 vector is in W. So our job really, if we're trying to show that W is a subspace, the expectation on us would be to address that, but we don't have to say any more to justify it. By properties 2 and 3, you want to justify carefully. So remember what the second property is. The second property is that the space W is closed under addition, meaning that if you take 2 vectors x and y and assume that they're in W, you got to somehow conclude that their sum is in W. Right? So we're not going to proceed like we did in this box where we just start writing down random vectors and adding them together and just play around. We're going to try to prove that this is true in general. So the way that works, and actually let me just add a little bracket here just to indicate that is the proof, or at least the acknowledgement or justification that the set W satisfies condition 1 of a subspace. But now we're going to show that it also has condition 2. So we're going to start by assuming that we have 2 vectors in W. Let's start with that assumption. So the way you would start that is to do something like this. Let x and y be in W. And it just turns out to be convenient to get in the habit of not just saying let x and y be in W, but actually write out some coordinates for them. Give them some coordinates or give their coordinates some names. We're not going to pick specific numbers for the coordinates, so that wouldn't work for us. We have to stay general. But it's nice to have symbols that we can use to refer to their coordinates. So what I mean by that is just do something like this. Let x be the coordinate vector x1, x2, and x3. How about that? And then, so let's assume that that is in W. And then we also have a vector y in W. So I'm going to write y, and then I'll give it some coordinates. I'll call them y1, y2, and y3, and we'll assume that that's in W. Okay, so really all we've done is we've assumed that we've got 2 vectors, x and y, in W. Okay, well, what does that mean? What can we say about the vectors x and y, right? We didn't say that there are any vectors in R3. We said there are any vectors in W. So that means they have to satisfy a certain condition. They both need to satisfy this condition, meaning that their second and third coordinates must be equal. So in other words, x2 and x3 must be the same. y2 and y3 must be the same. So let's explicitly spell that out, because that's going to be your automatic next step. As soon as you start by assuming you've got 2 vectors in W, your very next step is going to be to actually spell out what that means. What can you get from that? And this is what we can get from that. We can say then we know that x2 is equal to x3, and y2 is equal to y3. Okay, so that's about as much as you can say though now. So what next? We'll go back to what our goal is. We assumed that x and y were in W, and now we want to show, this is the part that we need to prove. We need to prove that the sum of x and y is also in W. Well, let's start by actually writing out what the sum of x and y is. So let's write out x plus y, and we'll just add those two vectors up, right? We've got coordinates for x and we've got coordinates for y. So let's add them together. The first coordinate is going to be x1 plus y1. The second coordinate will be x2 plus y2. And the third coordinate will be x3 plus y3. Okay, so that is our x plus y. We need to justify and convince whoever's reading our work that x2 plus y2 is equal to x3 plus y3. And typically what you're going to use at this stage, and you might already see why it's true, and that's great, but try to think about this procedurally. In general, once you get to this stage, you're going to need to look for evidence to conclude that this vector actually is in W. And typically it's going to be this line here, where you wrote out the consequences of x and y, or x and y belonging to W, right? That was this line where you actually wrote out what that meant. Typically this is where the information is going to be that you use to justify that this is actually in W. But here's how I would say it. X2 plus y2, we need to show that this is equal to x3 plus y3. Let's be really careful and really rigorous here. Let's do the following. Let's write this is equal to x3 plus y2. Well, what did I do there? And is that true? That wasn't a typo or a mistake, right? The idea is this. From this first equation, x2 is equal to x3. Well, if x2 and x3 are the same thing, then I can take this expression x2 plus y2 and just replace it with x3 plus y2 without harming anything. And they're going to be equal because these two things are equal. So that's okay. Let's now, going from here, let's now apply this equation to this expression. And in other words, replace the y2 with a y3. And we're going to get x3 plus y3. And now if we combine these two equations, or these two links in the chain, you get x2 plus y2 is equal to x3 plus y3. And that's a strong justification. So let's say, how about we add it in here? Therefore, x plus y is in W. Okay, so that completes the justification that W satisfies the second condition, because we started with the assumption. This part, it's important to notice the difference between an assumption and a conclusion. This line was where we made an assumption. We assumed that the vectors x and y were in W. The next step was we wrote out what that meant. Then our next line, what do? We just added x and y together to see what we would get. And then our fourth line, we actually justified using our assumption. This is really part of, this comes right from the assumption, so this, you might as well call this part of your assumption. We use this assumption to conclude that x2 plus y2 is equal to x3 plus y3, and that was how we justified that this vector is actually in W. So then here we stated our conclusion. So that's how you can organize your work clearly so that it's easy for the reader to tell, first of all, that your work is correct, and then second of all, they can see why this W satisfies each condition. So far we've got the second condition written down, or justified fully. Let's look at the third one now. So what's the third one again? Remind yourself, just look back at the definition. If you have any vector in W and any scalar k, then the scalar product of k times that vector has got to be in W as well. So our assumption is going to come from here. We're going to assume that we've got some vector in W and some scalar. So let's start with that. So let's let the vector x, and again we'll write out coordinates just like we did before. So let x be a vector in W and k just be any scalar at all. That's our assumption. We're not proving this, we're just assuming it and seeing if we can use it to justify the conclusion of statement 3. Okay, well let's make it a knee-jerk reaction. Once you finish that line where you start with the assumption, write out exactly what you get from that, just like we did at this line. Right? We started by assuming x and y were vectors in W. The very next thing we did was write out whatever consequences we could derive from that. So do that here as well. Now, since we only have one vector, right, there's no y this time. There's just a vector x. So the only conclusion we can get from that is x2 is equal to x3. Okay, well, now let's look at the conclusion we have to show. Right, we have to derive this conclusion. We have to show that kx is in W. Well, let's work out what kx is. Let's write it out in terms of its coordinates. If I write down kx, well, what is multiplication by a scalar? It's just going to multiply each of those coordinates by the scalar. So we're going to get the vector kx1, kx2, and kx3. Okay, so we need to show that this is in W. Why is this in W? Well, the second and the third coordinates, are they going to be equal? Well, because we know that x2 and x3 are equal, right? We know that from our assumption. We assume that x was in W. We can assume that x2 and x3 are equal. So based on that assumption, if you just take this equation and multiply it by k, well, you're going to get kx2 is equal to kx3. So let's just write it this way. Since kx2 is equal to kx3, and really, what's the justification? This is, we didn't need to say too much more, because really this immediately follows from this line here, right? If you multiply both sides of this equation by k, you literally get this one. So there's not too much that we need to say, aside from just addressing the fact that kx2 is equal to kx3, and that is in fact exactly the condition that we need, right? These two coordinates being equal to say that this vector is in W. So we can say since kx2 is equal to kx3, kx is in W. And that finishes our justification for the third statement, right? Because we assumed that x was a vector in W and k is a scalar on this line. And then we were able to conclude now on the fourth line that the scalar product of k times x is also in W. So that's why this is now a complete proof of the third condition. So we've worked out all three conditions, we've justified them all. Now we can make our conclusion and say, therefore, W is a subspace of R3, right? Because it's a subset of R3. So that's why you're not going to say subspace of Rn, which you could say that. It's technically not wrong, but it's a bit sloppy. We should be more specific, because we know that the vectors in W are three-dimensional vectors. So we'll say it's a subspace of R3. Okay, so that is an example of how, if you're given a subset of Rn and you're asked to show that it's a subspace of Rn, then that'll be the approach you use. Just verify the three conditions one at a time. Okay, our next example, we're given a subset of R4, right? We're given a set W, which consists of vectors which have 4 coordinates, which must satisfy this equation. Right, so this one is a little bit more complex, right? W is the set of all 4-dimensional vectors such that, well, 2 times the first coordinate plus the second coordinate minus the third coordinate plus 3 times the fourth coordinate is equal to 0. That's how you should think about this, right? Notice I avoided saying W, X, Y, and Z, because those are just dummy variables or placeholders used to represent coordinates. Really, the thing that you would need to check to show that a vector is in W is that 2 times the first coordinate plus the second coordinate minus the third coordinate plus 3 times the fourth coordinate is equal to 0, right? You wouldn't need to even mention W, X, Y, or Z. But this one doesn't say show it's a subspace. It says determine if it is a subspace of R4 or not. So it's a little bit open-ended. Maybe it is, maybe it's not. Well, what are we supposed to do? Right? Are we supposed to show that it's not, or are we supposed to prove that it is? If it doesn't tell you in advance whether it's a subspace, how are you supposed to know what to do? And that's the nature of a lot of mathematical questions. If you don't know the answer in advance, you're not always going to know what strategy to use. And so you have to really just pick one, try to work on it, try to prove it, and be willing to accept the fact that you might be trying to do something impossible. And if it starts to seem really hard, if you spend a few minutes on it, it seems like you're hitting a brick wall, well, then maybe that's evidence that you've picked the wrong conclusion to try to draw, and maybe you should try to justify the opposite. So in this case, that's more general, but in this specific case, why don't we do this? We'll just start trying to show this is a subspace of R4, just like we did in the previous example. But if we hit a brick wall at any of the conditions and it just seems like they're not going to work, well, then maybe we'll start to believe that this is not a subspace of R4. And if we get to that point, then maybe we'll try to show that one of the conditions fails. Well, if you're going to try to show that W is not a subspace, if we get to that point and we decide we're going to try to show that W is not a subspace of R4, well, then which one of these three conditions are we going to try to show fails? And well, if we had gotten stuck on one in the first place, maybe that would be a good place to start, right? If we got stuck on one of these conditions while we were in the beginning trying to show that W is a subspace, and we got stuck on one of the conditions, well, that's probably the first one I would look at to try to look for when it might fail. If I change gears and try to show the opposite conclusion, trying to show that W is not a subspace of R4. Okay, so if some of that's a little bit confusing, don't worry too much. The important part, to get back on track, the important part to know is we're going to try to show that this is a subspace, and we're just going to see if we are successful. If we're not successful, then we'll deal with that. But if we are successful, then that means it worked, and we're done. So let's start with the first condition, which is that the zero vector be in W. What's the zero vector in this case? The zero vector, we're talking about a subset of R4, right? It's got four-dimensional vectors. So we want to know if the four-dimensional zero vector is in W. Well, is it in W? Well, if I plug these four numbers in for these four numbers, or in other words, if 0, 0, 0, and 0 get plugged in for W, X, Y, and Z respectively, will it work out to be 0? And of course it will. If you plug in 0 for every single variable, you're just going to get 0 on the left-hand side of this equation. So you're going to get 0 equals 0, which is a true statement, which means that this vector is in W. And just like in the last case, there's not much else you can say to that. Okay, so well, that's the first condition. So the first condition succeeded. That doesn't mean it's going to be a subspace, but put it this way, if it ends up not being a subspace, we know it's got to be one of the other two conditions that fails. It's got to be either condition 2 or condition 3 that fails. Okay, so what now? Let's start by choosing two vectors in W. We're really just going to start out the same way we started this one, right? We're going to start by choosing a vector X and a vector Y in W. And you don't have to call them X and Y, by the way. You can call them whatever you like for the purpose of your argument, but just make sure to be consistent with the notation you use. Like, for example, here we could have said let U be equal to U1, U2, U3 be in W, and let V be the vector V1, V2, V3 be in W. And then we'd have to modify the rest of our work to be consistent with that notation, and our conclusion would have been that U plus V is in W, and that's totally fine as well. You have some freedom to change your notation, but just be consistent and be precise. So, and if in doubt, if you're not sure what liberties to take, well then just for now, don't take any liberties and just follow these examples exactly for the moment. As you master this process, you can start to get your own style. But until that point, it's best not to deviate from this. Just start by doing this exactly the way I show you for now. And then, like I said, once you gain mastery, then you can start putting your own style and your own spin on some of these steps. But let's follow it exactly for now. So we'll let X be the vector X1, X2, X3, and X4. Right? I'm just writing down a general four-dimensional vector. So assume that that is in W, and we've got a vector Y in W, which I'll label as Y1, Y2, Y3, and Y4. So we're going to assume that those are in W. Okay? Well, what do you do next? Write out what that means. What does it mean for X to be in W? These four coordinates need to satisfy this equation. If I plug in X1 for W, X2 for X, X3 for Y, and X4 for Z, then I have to get 0 for the left-hand side of this equation. So what this means is that 2 times X1 plus X2 minus x3 plus 3x4 is equal to 0, right? And 2 times y1 plus y2 minus y3 plus 3y4 is equal to 0. That comes from the assumption that y is in W. It means these four numbers have to, when plugged in for these four variables, this equation ends up being satisfied. So that's where this equation comes from. Okay, so that's what it means to spell out what it means for x and y to be in W. Really, it's the analogous version of this line for the previous example. All right, well now we need to show that x plus y is in W. So let's start by working out what x plus y is. So we're going to have x1 plus y1, x2 plus y2, x3 plus y3, and x4 plus y4. So that's what x plus y is. Now we need to check, is this vector in W? Well, what does it mean for this vector to be in W? What do we have to show? We have to demonstrate that these four coordinates, if we substitute them in for W, X, Y, and Z respectively, then this equation ends up being true. So how about this? Why don't we just take this equation, or the left-hand side of this equation, and plug in x1 plus y1 for W, x2 plus y2 for X, plug in this for Z, plug this in for Y. I think I said that wrong. Let me start over. Plug this in for W, plug this in for X, plug x3 plus y3 in for Y, plug x4 plus y4 in for Z. Well, what do we get if we do that? Well, we're just going to go 2 times x1 plus y1 plus, then the second coordinate is, I'm going to put brackets around it even though it's not strictly necessary, x2 plus y2, and then minus x3 plus y3, and then lastly plus 3 times the fourth coordinate, which is x4 plus y4. So really, that is the left-hand side of this equation if we plug in these four coordinates for w, x, y, and z. That's what you get. Well, now what? Is this equal to 0? Let's try to prove that it is. And how would you do that? Well, we only have these two assumptions to work with, right? We're assuming that this equation is true and this equation is true. So maybe if we expand the brackets, like distribute the 2 and the negative and the 3 into the brackets, maybe we can somehow put these two equations to use. So that's usually the attitude you go into this with. So the next line, we're going to distribute the 2 into the brackets. We'll get 2x1 plus 2y1 plus x2 plus y2. That negative will be distributed into the brackets, minus x3 minus y3. And then lastly, plus 3x4 plus 3y4. Okay, that's a 4 there. It looks a bit weird, but that's 3y4. That's what that's supposed to be. Okay, well let's group all our terms, right? Let's group all the x terms together and then see how it looks, how it compares to this equation, and we'll group all the y terms together. So we'll get 2x1 plus x2, so I'm taking that first term, ignore this for now, take the x2, ignore this for now. We've got x3 minus x3. We'll ignore the y term for now, then finally plus 3x4. So that is all the x terms. And then what about the y terms? We've got 2y1, so I'm going to say add that term on after, plus 2y1. Y2, we've got plus y2. We've got minus y3. And then the last one is plus 3y4. There, that one looks a little bit better than the previous one. Okay, so that's our y terms. And now what? Can we use our assumptions at all? Looks like we can, because this is exactly what you see on the left-hand side of this equation. And if we're assuming that this equation is true, then this must be equal to 0. So that simplifies things greatly. And same with this, actually, 2y1 plus y2 minus y3 plus 3y4. If we're assuming that this equation is true, then this has to equal 0. So what we really have here is just 0 plus 0, which works out to be 0. So we did it. That means this ends up working out to being 0, which means that this vector is in W. So we can now say, therefore, x plus y is in W. So this is starting to look like this is going to work. And I'm starting to feel pretty confident myself. So this is the first condition. We checked that one, right? The 0 vector's in W. And now we just finished checking the second condition, because we assumed that x and y were vectors in W, and we were able to successfully prove that therefore the sum of x plus y must also be in W. Okay, so that's the conclusion for the second statement, right? I'm going to put a box around it, not because it's a final answer or anything, that's why I'm using green, but just because it's an important part of this portion of our work. So on the next page, let's try to prove the third condition. And if we can prove the third condition, then that means it works, and that means W is a subspace of R4, and that means we'll have our answer.